Is this just fantasy? Oh, hello there. Hey guys, what's going on? A memes here. And as you can see from the title there, this is not just clickbait, or at least I don't think it is. Why do I say this? Because it was brought to my attention via the algorithm that apparently they had posted a presentation from Brown University Physics Department about twisted bilayer graphene and some very interesting properties that it showed at about a 1 degree angle, which was their magic angle. Let's listen.
So what happens in twisted bilayer graphene? So if you look at this diagram I've got here on the left, this is from the first experimental paper back in 2018 that was published on TBG.
Oh, there's a little dome there.
What they're doing here is the resistivity as a color as a function of temperature and carrier density.
Temperature and the density.
So the red regions are regions with high resistivity, the blue regions are regions with low resistivity, and the dark blue is where the resistivity is.
I believe he's saying resistivity, basically the amount of resistance there, which standard copper wires and everything, you're gonna get some resistance. It's gonna go off into heat. That's why we have to have like different power stations, very often using petroleum or carbon-based things, because, well, the sun's not always shining. It's shining somewhere, but it's really far away. Wouldn't it be cool if we could send power all the way across the world where the sun was actually shining? Maybe we could actually do some cool things and be good shepherds for the planet. I'm just saying. Continue.
Is essentially zero, meaning you've got a superconductor. And
a superconductor.
So this is the experiment that generated so much.
But a superconductor, technically, you're not supposed to have any of that energy loss. Are you saying we could actually send power around the world? Hypothetically, of course. Continue, sir.
Attention, because you saw the superconductivity, which was quite unexpected.
Something unexpected.
And then you notice that next to the superconductor in this red region, they've denoted a phase MOT. So
what? Like the apple.
A MOT insulator is an insulating state that comes from electron-electron interactions. So
we're not going to go through the whole thing. The whole thing is in the doobly-doo. I like it. I like science, but we're going to cut to the juicy snippets. All right. So it was 924. Oh, 1438. Continue.
What's the quantum Hall effect? Well, you just take a two-dimensional slab of metal and apply a large magnetic field perpendicular to that metal.
Those
look
like...
What happens if you just solve the single particle problem is that your energy levels...
Why does that look like the valence levels of an electron or something? I'm not sure if it has that many states. I think it has 4 orbitals. I could be incorrect. I think you're allowed to have more in different ones.
Form these so-called Landau levels. And the important thing is that these Landau levels are completely flat. Okay, and so you've got these highly degenerate flat Landau levels, which mean that the kinetic energy is essentially quenched in the system. And so, of course, this leads to very strongly interacting physics because there's no kinetic energy whatsoever. It's completely dominated by the interaction energy, which is just going to be the electron-electron Coulomb interaction.
Now, again, I do not work for Brown University. I'm a science enthusiast on this Internet of Stuff and Things. But what it kind of sounds like the way they're kind of able to get away with this is basically graphene. You kind of just print it off, or you take the Scotch tape and you literally hold it on, kind of like the pencil thingy. And I'm like, that's very interesting. If only we could find better and better ways to mass produce this. But essentially, it's technically two-dimensional, at least from some perspective, because you have the individual carbon atoms. But if you take 2 layers, and you just slightly twist them a little bit, it basically ends up forming a whole lot of hexagon spoilers. And apparently that lattice ends up, the electrons basically at a particular level will continue on. They experience superconductivity.
And so if you have this Landau level, you put in some electrons, then on the non-interacting level, it's going to be a highly degenerate problem, but then you switch on the interactions, and you get some interesting states, such as the fractional quantum Hall states.
It's a beautiful thing.
And it turns out that the physics of twisted bilayer graphene is very reminiscent of this sort of Landau level physics as well, in the sense that you have extremely flat bands. So if you just look at this band structure I've got in the center, then this is a certain limit of twisted bilayer graphene, but you can see that the energy band is completely flat. So there's no kinetic energy whatsoever.
And so basically, temperature is, it's basically what you crank up the temperature in a room, you're going to get some more oscillation. You're going to get the movement. If you can limit that, and what's the best way to limit it? In the simplest thing possible, what are you doing? You're taking a 2D surface, you're enhancing it with another 2D surface. It's like, let our powers combine. And now we might be able to do some incredibly amazing things.
And this looks exactly like a Landau level. And in fact, the connection goes a little bit further. If you compute the Chern number of these bands, they have got plus minus one Chern numbers.
Minus one. How very convenient.
Which essentially looks like you've got Landau levels, two Landau levels in an opposite magnetic field, essentially.
Okay.
The interesting thing to notice about this figure is that you get these
a very small range.
Insulating states at every integer filling. And the ones at +4 and -4 are quite bogying band insulators. That's not difficult to understand.
The thing with superconductors, typically as we find them, they need to be extremely freaking chilly. They had one that I think was available that was like 52 degrees Fahrenheit or something. Something that was kind of like a roundish room temperature. There was one catch. It needed to be at like 10 million psi or something like that. You need to have a diamond press on this material. It was still a cool idea, but somehow I think if we could ramp up, I don't know, printing of graphene and get our engineers to do some science on it, the materials folks, and especially since we have fabs working everything where it's like, oh, wait a second, temperature, if we can account for that, maybe we can better account for charge and everything. I think we have the people. No, I know we have the people. I totally think we can do this. I totally think we can continue. Shout out to my patrons, Dave M. and Joe Franco. This broadcast is helped made possible by viewers like you. Ain't nothing wrong with the PBS model.
What's more interesting is that you also get insulators at every other integer filling, -3, -2, -1, 0, and so on. And
wait. Okay, I think I noticed this before, but I'm like, wait a second, 4 levels? It's going in the different directions. That kind of reminds me of an electron.
If you just look at the band structure, well, you wouldn't expect to get an insulator there. You would expect to get a metal because your chemical potential is somewhere in between these bands. So instead, to explain these insulators, we need to include interaction physics. And that's why we call them correlated insulators, because there's some sort of correlation physics that leads to...
Again, I do not work for Brown University, but I think this is why in physics very often, like I've heard at least Ed Witten enough times, the guy that's won like the Fields Medal, which is essentially like the Nobel Prize in mathematics that we have. It's like he's very often going from a 2D state and then you translate things out into 3D. Why? Well, it's typically easier to work in 2 dimensions. It's less complicated, usually, as far as I understand it. But you're taking a 2D thing that maybe we could better model classically. Maybe we don't need to get all super fancy. It's like, okay, we can kind of tell what's going on. We have a repeating pattern. You're just going to keep smiling around. And I'm like, we could probably make this work. Continue.
An insulating state. And
important.
In between these correlated insulators, we see these superconducting domes. So this is sort of the experimental feature that we want to
as well if we have the technology.
And so the model that we're going to use is to take the band structure of twisted bilayer graphene.
I'm not saying that looks like any type of vortice equations or anything. I really haven't looked at it, but sometimes you start seeing familiar things there as well. What is it? Were we already there? Integer. Yeah, we were. All right. So we go back down. I found this interesting. I found this the second time.
But let me just skip the slide.
So we're gonna skip the slide. Why does he skip this? Because again, I do not work for Brown University and have not done a PhD in physics. But the model is U2K times U2K equals about UC1 times UV1 times SU2K times SU2K. I believe those are the two kind of graphene-based surfaces, and then basically you have whatever, I assume current or whatever is there. So essentially, since it's a two-dimensional surface for our purposes, neglect single particle dispersions equals pH, or at least the pH symmetry. And again, these are things where we there's a lot more to learn. Neglect incomplete sublattice polarization, at least the chiral symmetry. You hear that word a lot in physics. Enhanced U4 by U4 symmetry. So wait, you took SU2 and SU2, you layer it up, and you get enhanced U4. I totally love it.
It's a bit technical.
But all right, last part here, and
where we sort of throw out some of the terms in the Hamiltonian that are at smaller energy scales. We just focus on the largest energy scale. And in that limit, we can sort of exactly derive what the ground state is.
Just notice what that says there. You look at, don't worry about any of that. Again, I'm looking at this. You're looking at the levels of the energy levels. It's like, all right, you want to go up to the higher electron volts. It's probably easier for us to figure it out rather than trying to go on the super small level. But that will probably be also very interesting in how that could be worked out later. But it's like, all right, interlattice interaction, inter-sublattice hopping, inter-sublattice interaction, inter-sublattice hopping. It's almost like, depending on the energy level, it's like you get the interaction, this is kind of skipping around. I just find it fascinating.
What the ground state is. And essentially we find 5 different types of ferromagnet.
5.
So
it's a good number.
I'm listing the 5 types of ferromagnets that you can get here: KIVC, quantum Hall state, Valley polarized state, Valley Hall state, and time reversal invariant intervalley coherent
I have
state.
no idea what any of those are.
I don't worry too much about the details on the slide. I don't want to go into too much detail here, but I just want to say that we've got these 5 degenerate types of quantum Hall ferromagnets, or generalized quantum Hall ferromagnets, that are known to be the ground states in this idealized limit. And then if you add the sort of subleading terms to the Hamiltonian that I was
Hamiltonian is basically the fancy word saying, all right, we understand certain parameters. I think it's like charge and like angular momentum or something like that. Because if you can get those down, it's like, if you can get mass and everything else, you can figure out a lot. But I'm just saying. That's my understanding.
Neglecting before, then they actually pick out one of these ferromagnets as the true ground state, and this is this so-called KIVC state. But as I said before, it's just one of these strong coupling ferromagnets.
I love it.
And so for quite a long time, it was believed that these strong coupling ferromagnets are just these correlated insulators that are observed. And I want to argue that, in fact, these strong coupling ferromagnets are not the whole story. In fact, we need to consider these so-called incommensurate Kekulé spirals. So
we're going to skip ahead
a couple of realistic perturbations.
Okay. Basically, we start getting fancy. Again, I love this stuff. Totally check it out if you want. But basically, you're seeing sort of symmetries. Basically, depending on how you have it angled and everything. Where does he have it? It's I used it in the initial screenshot. But essentially, what ends up happening, you end up getting these patterns. You get these patterns and everything. So it's like, all right, the electrons and stuff can kind of zip along this way, zip along that way. I'm like, if you can get that to work, then again, it's like, you're probably going to have to do layer over layer if you want to do large-scale power. Almost maybe twist it in a way, but you're probably going to have to use something else as well. Now, again, I was thinking, I'm like, oh, maybe some sort of gel or something like that. I'm like, do you necessarily need it? But then we came across, hold on, I gotta reshare here. Bada boom, fractal woman. I almost said fractal girl. I apologize. I believe that's physics girl, or is it physics woman? Oh my god, I'm not giving people the credit that they're due. I'm just gonna do the window over here because there's no sound. But yes, as we can see, she had this video. She's been writing a paper and basically doing some work with ferromagnets. What is a ferromagnet? We'll get into that in just a moment. It's essentially something that you can kind of print, and then if you have different magnets around, you can basically show their effects. I think those are neodymium magnets. But what I ended up noticing, I'm looking at those patterns, and it kind of started to remind me of some of Thad's work as well. Basically, when he was showing out those different vortice tubes and stuff, I'm like, that's very interesting. Yeah, it was right around the transition point, just because it faded to a shade that just kind of just it triggered in my memory as well. But kind of along there, yes, yes, you see, and then it goes through the butterfly effect. But what is a ferrocell? It's brought to us by ResearchGate, also in the doobly-doo. Look at all those fancy schmancy spirally thingies. The ferrocell left and the ferrocell fitted into a 3D printed frame right with the LED a light strip inside the periphery. Cube magnet placed in the top. B. Cube neodymium magnet placed in under contact. Activated ferrocell. Notice under magnetic viewing, the body of this magnet becomes transparent, i.e., a visible cloak. And only its magnetic flux is shown. The magnetic flux, you say? Don't we call it electromagnetism? Hey, now. I see you there, Drew. Good to see you, my friend. I'm just saying that it really would be a shame if we just destroy ourselves when we're actually like on the cusp starting to solve like some of the greatest problems in humanity with like new science and everything. We're going to see like a second Einsteinian like evolution, or excuse me, just whatever, just the future of science. I'm just saying. We're going to continue. But essentially, you go through what they're doing right now is they're kind of like almost like 3D printing, basically you 2D printed essentially, and basically you have the magnetism and everything. And then, because I like the Googles and the Wikipedias, I totally need to support Wikipedia. But ferrofluid, oh, ferrofluid is a liquid that is attracted to the poles of a magnet. It is a colloidal liquid made of nanoscale ferromagnet or very magnetic particles suspended in a carrier fluid, usually in an organic solvent or water. Each magnetic particle is thoroughly coated with surfactant to inhibit clumping. That sounds like a form of lubrication that stays with it. Better safe than sorry. Large ferromagnetic particles can be ripped out of the homogeneous colloidal mixture, forming in separate clump of magnetic dust when exposed to strong magnetic fields. The magnetic attraction of tiny nanoparticles is weak enough that the significance of van der Waals force is sufficient to prevent magnetic clumping or agglomeration. What does that even mean? Uh, Fluctuation in the field chemistry is process chloroplast come a suspension of sediment. Oh, it's kind of like shaking up sand at the bottom of like the beach when you're in the water a little bit. Ferrofluids usually do not retain magnetization, the absence of an externally applied field, and thus often classified as super paramagnets rather than ferromagnets. Guess what? It's not a turtle. It's ferrofluid. But we're going to be computationally equivalent. I don't know. Are they both made of stuff and things? I think they are. See, you got a little magnet under there, so it's kind of just going through, projecting itself up there because they got the glass and everything. I remember the Vortex Institute totally did something like that. That was another YouTube channel that put videos and stuff on. It's amazing how everything comes together. In contrast to ferrofluids, magnetohydric fluids, MR fluids, are magnetic fluids with larger particles. I think that's what this is. No, that says ferrofluid. That is a ferrofluid contains primarily nanoparticles, while an MR fluid contains primarily micrometer scale particles. That is, several magnitudes of order higher. The particles in a ferrofluid are suspended by Brownian motion and generally will not sunder under normal circumstances. While particles in an MR fluid are too heavy to be suspended by Brownian motion, particles in MR fluid will therefore settle over time because of the inherent density differences between the particles in their carrier fluid. As a result, ferrofluids and MR fluids have very different applications. Okay, they're going over the inventor, which was, I believe, Steve Papel, invented ferrofluid for NASA in 1963. All right, that's really cool. What does any of this stuff mean? All right. It is, in my opinion, as a dude that's a science enthusiast on the internet, we can help utilize this technology to help get power a lot more effectively across the world. We're still going to be able to generate it by plenty of ways, but all I know is with new science comes new opportunities. And we got plenty of folks out there in the science community. Scientists? What's science? Why? Because we can. And I think it would solve a lot of problems. But the interesting thing in there, I just kind of read about the MR fluid as well. I'm like, all right, so within standard electricity transfer, as far as I understand it, the things you have in your house, you're probably going to have between, I don't know, like 240, someplace 277, something like that, and you break it down. And then you got the high voltage lines and everything like that. Whatever that is, however many volts and amps and everything like that. It is actually kind of like pressure as well. You might have the volume, and then you actually have the amount of energy that's going through. I still don't necessarily know how it completely works. But all I'm saying is, all right, you have different structures that you're using. Now, depending on the scale of what we're trying to transfer, in some cases, maybe you want to use some smaller particles. Maybe we could use some of that ferrofluid, or maybe something kind of like that, acting as, I don't know, maybe some form of a lubrication, maybe a conduit, because I don't know, will we throw things out of whack when we do more than 2 layers of graphene? Might we need some form of an additional insulator on top of that? Maybe we just graphene all the way down. All I know is I watched a couple of videos on the internet. These things were recommended, and it got me to really thinking. I'm like, well, if you got the electricity transfer, could we make it go both ways? I don't know. Would that be more effective use of resources? We're going to need a lot of computers to keep track of that, because all I know is apparently there was an issue with a gas line and a bunch of houses got destroyed. People lost their lives up here. I'm just saying that I'm sorry to leave on sad note, but all I'm saying, I see you there now. Don't worry. Great things are coming within science. We just got to learn from the past. Well, that's the thing. That's the story of humanity. It's to overcome. It's to level up. It's to not let what's in the past just hold us back. No, we learn from that. It sets the bounds of what we actually know. It's like all these folks, they did all these things. Okay, it didn't work. All right, now we know maybe that didn't work. Maybe there are things that we can do. Maybe the person that attacked that saber-toothed tiger with a non-pointy stick, maybe they got mauled to death. Maybe that's where we got 40 sticks from. Oh, good. I just invented war. I apologize. But hey, these things happen. Hopefully, we can do better in the future. But all I know is FDI. One thing at a time. One thing at a time. Let's take care of the resources problems as well, Drew. And we'll get to that. I'm not saying it's not possible. I think even Professor Wolfram said that it might be possible. And I trust Professor Wolfram a good deal. Why do I do this? Well,
it's turtles all the way down.
I was able to get that clip, so it totally means it must be true. Isn't that how the internet works? I don't know if that's how the internet works. But thank you all for watching. Peace out, everybody. And whenever it comes to science and everything,
come on and get your log. Everyone needs a log. Come on and get your log. Everyone needs a log. Log from Blammo.
We are not actually sponsored by Blammo yet. Thank you, Jen. Logs are apparently important within science. But see you, everyone.
Have you guys checked out the Memes of Destruction's channel? he's an interesting dude. I like him.